In today's lecture, we discuss the new topic, that is rotational dynamics. In previous standard, we defined the different types of motion: circular motion, rotational motion, linear motion, translational motion. These are the different types of motion. Now we discuss about the circular motion. In 11th standard, we define the circular motion. Circular motion is nothing but a particle. This particle is revolved around the circumference of circle. This particle revolves around the circumference of circle, or this OP is nothing but radius vector. The circular motion is very simple one. The particle or object revolve around the circumference of circle. This is called circular motion. Now there are some properties of circular motion. The first property is the circular motion is a accelerated motion. It is a accelerated motion. Its velocity changes at every instant of time. Suppose we consider A, B, C, D 3 points, and the particle is revolve around this circumference. At point A, this is the direction of velocity. At point B, this is the direction of velocity. At point C, this is the direction of velocity. And at point D, this is the direction of velocity. That means at every point on this circumference of circle, the direction of velocity is changes. That is, it is a accelerated motion. Second, it is a periodic motion. It is a periodic motion. That is, the particle repeat. Suppose this particle complete one round, second round, third round. This particle revolve around the circumference of circle with suppose center O, radius vector R. The radius vector is constant, and this particle repeat its path. This particle revolve around the same path, hence it is a periodic motion. Now we discuss some kinematics about this circular motion. The kinematics of circular motion. In previous standard, we discussed about the kinematical equations. There are 3 kinematical equations. Now, in linear motion and in circular motion. We know that in linear motion, the displacement of particle is denoted as s, and velocity of particle is denoted as v, and this v is equal to ds upon dt. Also, in linear motion, the acceleration is given as a, and acceleration is equal to dv upon dt in linear motion. But in circular motion, the displacement is nothing but it is called angular displacement, and it is denoted as theta or d theta. In circular motion, the angular velocity is denoted as omega, and it is given as omega is equal to d theta upon dt. And angular acceleration, it is denoted as alpha, and this alpha is given as d omega upon dt. In linear motion, the same displacement, velocity and acceleration, but in circular motion, the particle P revolve around the circumference of circle. Suppose this is the radius vector center O. This is the first position of particle. At some time, particle moves from point A to point B. The radius vector is same. Then some angle is traced by this particle due to this radius, and this angle is called theta or d theta, and this is nothing but it is called angular displacement. The particle is displaced from A to B, makes some angle, that is theta or d theta, from this center using radius vector, and that angle is called angular displacement. In circular motion, this is in short we say that the kinematics. In kinematical equation, in linear motion, the first kinematical equation is P is equal to u plus at, where v means final velocity, u means initial velocity, a means acceleration, t means time. This is the first kinematical equation. S is equal to ut plus half at square. This is the second kinematical equation, and v square is equal to u square plus 2as. This is called third kinematical equation in linear motion. Now we discuss about the kinematical equation in circular motion. The first kinematical equation in circular motion is denoted as omega is equal to omega 0 plus alpha into t, where omega means final angular velocity, omega 0 means initial angular velocity. This is the first kinematical equation in circular motion. Now second, theta is equal to omega 0 into t plus half alpha into t square. This is called second kinematical equation in circular motion. And last, omega square is equal to omega 0 square plus 2 alpha into theta. This is called third kinematical equation in circular motion. This is the kinematics of circular motion, or analogy of linear motion and circular motion. Now we define the simple definition, that is uniform uniform circular motion, in short UCM. It is also called UCM. The particle P revolve around the circumference of circle. It is called circular motion, and when the speed of particle is same or constant throughout or during motion, during circular motion, the speed of particle is same or remain constant, then that type of circular motion is called uniform circular motion. In uniform circular motion, speed of particle is same or remain constant. Now this is the direction of radius vector. Now also this is the direction of angular velocity. This is the direction of linear velocity, but this is the direction of acceleration is opposite to direction of angular velocity, and that acceleration AR bar is called radial acceleration, and this radial acceleration is constant in this uniform circular motion. Now we define the non-uniform circular motion. Non-uniform circular motion. In non-uniform circular motion, the particle is revolve around the circumference of circle, but its speed is increasing or decreasing. For example, if the fan is on or off, if fan is on, the acceleration of blade is increases or velocity increases, and if fan is off, the velocity of blade is decreases, and at certain time it is tends to 0 or it is stopped. That means in case of fan, this is the example of non-circular motion. In non-circular motion, the particle revolve around the circumference of circle, but its speed or acceleration is not constant. In non-uniform circular motion, this radial acceleration is not constant, hence it is converted, or there is another acceleration. We say that A bar t, and that acceleration is called tangential acceleration. This is about the uniform circular motion. During circular motion, the speed of particle is remains constant or same. It's called uniform circular motion. In non-uniform circular motion, the speed of particle is not constant, or this speed is increasing or decreasing. Now there is two forces is responsible for this uniform circular motion or circular motion. Suppose is the center O, radius r, and suppose this is particle, and this particle is revolve around the circumference of circle in anti-clockwise direction. Now we define the two forces in this circular motion. First is called centripetal force, or it is denoted as CPF. This is called centripetal force in the circular motion or uniform circular motion. The centripetal force is a force, or it is a real force, and this force is acting towards the center of circle from this particle, and that type of force is called centripetal force. Or in another word, if the particle revolves around the circumference of circle, the force is exerted from particle to center of circle through radius vector r, and that force is called centripetal force. Then this centripetal force CPF is given as minus m into a, where negative sign indicate that this force is particle to center of circle, that is opposite to the radius vector. Then we put the acceleration in circular motion. The acceleration is r omega square. Therefore, CPF is equal to minus m r omega square. This is the first formula of centripetal force. Second, CPF, we know that phi is equal to r omega. Therefore, omega is equal to v upon r. Therefore, minus m r, instead of omega square, we can write v square upon r square. Therefore, CPF is equal to r cancel, minus mv square upon r. This is another formula of centripetal force. The first formula is minus m r omega square m, where m is mass of that particle, r means radius vector, or omega square, or omega means angular velocity of that particle. Also in this formula, CPF is equal to minus m square upon r, where m is mass of particle, v means velocity of the particle. This is the centripetal force. The centripetal force is act to particle to center of circle through radius vector. The example of this centripetal force is the electron revolve around the nucleus, and every satellite is revolve around the planet. These are the examples of centripetal force, and centripetal force is a real force. Now, the second force in uniform circular motion is called centrifugal force, CFF. It is denoted as CFF, centrifugal force. Now we define the centripetal force in same figure. If particle is revolved around the circumference of circle and the force is moved, or its force is toward the center to particle, or this force is acted from center of circle to particle, or this particle is revolved around the circumference of circle, and a force is exerted from that particle from the center of circle to this radius vector r. That is, in this case, the radius vector and force is in same direction. Therefore, the centrifugal force CFF is equal to plus m r omega square, or centrifugal force is equal to m v square upon r. But this centrifugal force is a fictitious force or pseudo force. The example of this force is if the car turn, the passenger is moved in opposite direction of the turn of this car, or if car is start, the passenger moves back, or car is stop, the passenger is moved forward. These are the examples of this centrifugal force. The centrifugal force and centripetal force, there is some small difference. The centripetal force is center to particle, but centripetal force particle toward the center, but centrifugal force center to particle. And the formula and SI unit of this centrifugal force and centripetal force is same. Also, the centripetal force is a real force, it is pseudo force or fictitious force. This is about the centripetal force and centrifugal force in uniform circular motion. Now we discuss some application of uniform circular motion. Applications of uniform circular motion, and first application is the vehicle along a horizontal circular track. The first application of uniform circular motion, if the vehicle along horizontal circular track, suppose we consider a horizontal surface and suppose a vehicle is on this track, then suppose this is the center of this curve road, and now this vehicle on this horizontal road and performing uniform circular motion. Now the weight of that vehicle, the first force exerted on that vehicle, its weight acting vertical downward, or this is its weight when the vehicle on this horizontal circular track, the three forces acting on this vehicle, the first force, the weight of that vehicle acting vertical downward, that is W, is equal to mg. Second force, the normal reaction acting vertical upward, that is N. It is denoted as N. The normal reaction acting vertical upward, and the role of that normal reaction, this normal reaction balance the weight of that car or weight of vehicle, that is this N is equal to W is equal to mg, and this normal reaction is due to, or this normal reaction balance the weight of that car. Now third force is acting or responsible for this vehicle is called, it is denoted as FAS, and it is called force of static friction between road surface and tires of vehicle. This is the third force acting on this vehicle in this direction. Suppose this is a force Fs, which is called force of static friction between road and the tire of vehicle, and the magnitude of that force of friction is exactly equal to, or this force of friction is acts as a centripetal force, or magnitude of this force of friction is exactly equal to centripetal force, and centripetal force is equal to mv square upon r. Now suppose this is equation number 1, this is equation number 2. Now from these two equations, Fs upon n is equal to m v square upon r divided by mg, or this is equal to v square upon r into g. Fs upon n is equal to v square upon rg. Also, the force of static friction, the force of static friction is directly proportional to normal reaction, or Fs is equal to mu s into n, where this mu s is called coefficient of static friction, and its value is mu s is equal to Fs upon n. Mu s is equal to Fs upon n, or from this equation, Fs upon n is equal to v square upon rg. Therefore, mu s is equal to Fs upon n is equal to v square upon rg. Therefore, v square is equal to mu s into rg, or v is equal to under root mu s into rg. This is the maximum velocity, or is denoted as Vmax. This is the maximum velocity of vehicle when the vehicle is along the horizontal circular track, and when this vehicle is over this circular track, its velocity or its maximum velocity, it should be Vmax is equal to under root mu s r into g, where mu s is the coefficient of static friction between road surface and tire of vehicle, r means the radius of that circular track, and g means acceleration due to gravity. That's means this velocity of the any vehicle, there is no m. That means this velocity does not depend upon mass. Hence, this equation is applied to heavy vehicle or light vehicle. Vmax is equal to under root mu s into rg. This is the first application of uniform circular motion.